The goal of the talk of today is to give you, let's say, an introduction to the topic on which I work on in collaboration with Juan Naranjo at UB. So the title is Jacobians, Prime Varieties, and Moduli Maps. So I'm going to introduce the object in the first part and then to try to give you an idea of the problem we are facing with. So, yeah, the outline of the talk is the following. I'm going to speak about curves, complex curves, coverings, and abelian varieties. Then I will introduce you two famous moduli maps in algebraic geometry, so the Torelli morphism and, yeah, I mean, prime morphisms are more than one. It depends on the kind of coverings that you consider. So I'm going to speak about these two maps, and then I will focus on a particular kind of covering, which is called diedral coverings, and we will attach a problem on prime varieties related to this specific kind of covering. So, okay, the first object that we want to introduce is a curve. So since I work over C, for me a curve is a one-dimensional complex manifold. So it's the datum of two elements. So I need a topological space and a complex atlas, where a complex atlas is the way to give coordinates on the topological space. So it's a collection of maps defined on open subsets of the cover of the curve, and yeah, they are local homeomorphisms. So what I'm saying is that locally, a curve behaves like an open subset of the complex plane, but this is just locally. So what I ask is that the phi composed with phi j minus 1 is just the change of coordinates, and I ask that this is holomorphic. So locally, it behaves like an open subset of the complex plane, but the topology can be very different from the complex plane. Indeed, okay, since we ask that the change of coordinates is holomorphic, it is C infinite. So the point is that topologically, the topological space that we have when we take a complex curve is a two real manifold, which is not just C0, but it is C infinite. And so for this kind of topological space, we can use the classification theorem. So usually compact complex curves are called Riemann surfaces. And we have the classification theorem that says that these are classified by the genus, so by the number of holes. So when we speak about a complex curve, we have to think that in mind, we have to consider the case of the sphere, which is when we have genus G equal to 0. We have the torus, which corresponds to genus G equal to 1. This is the standard torus. And then we have a connected sum of G toral. So remember that to obtain these, what we do is, usually the picture that we have in mind is a square where we have moved all the complex plane inside this square. We are identifying these edges. So in this way, we get the torus. And this is just the generalization in case of G greater than 2. So we have to take a polygon with 4 G edges. And what we do is the same. So here we have A1, B1, this is A1 minus 1, this is B1 minus 1, and so on and so forth. And what we do is, okay, here we do the first identification of the first 4 edges, as we did here. So we get the first all, and so on, and so we get all the other one. And yeah, the point is that, okay, up to diffeomorphism, we can just use the genus to classify a real two-dimensional manifold, but this is no longer true when we move to C. So for this reason, we have a moduli space which is precisely the set that parameterizes the possible complex structure that we can have on a topological space of this kind. And yeah, when I speak about moduli space, the point is that moduli space are very used in algebraic geometry, and the idea is that you want to have a set where every point corresponds to an isomorphism class of objects. In this case, I'm considering the equivalence relation given by isomorphisms. And yeah, this is not just a set, MG, and indeed, I mean, Riemann was the first guy who studied it a lot, and he proved that it is not just a set, but it is an orbifold. So it's, let's say that it is a manifold with isolated singularities. And okay, of dimension 3G minus 3 when the genus is greater than 2. In the case of G equal to 0 is just a point, so we just have the sphere with the complex structure given by the projections by the two poles. And here we have, maybe Michele is going to speak about elliptic curves later, so here we have a one-dimensional moduli space. Okay, so we have one object in mind, which is a complex curve. And now we move to the other object, which are the abelian varieties. So to get the definition of an abelian variety, we have to first introduce a complex torus. A complex torus is a G-dimensional generalization of this torus. So in this case, what we have is that we are in C, we are taking two vectors, which are linearly independent over R, and the torus is precisely the identification of C mod out by the lattice, where the lattice is the one generated by these two vectors. So in C, we have all these points. So this is the lattice, blah, blah, no? So we move, all these points are identified, and what we get is the torus. When we work in dimension G, we have to do the same thing. So we have to consider lambda 1, lambda 2G vectors of CG, which are linearly independent over R. And then we define a complex torus as mod out by the lattice again. And the point is that it is nice as a complex variety because it inherits the structure of a group from C to the power G. So we can sum points on the Jacobian, on the abelian variety. And a complex torus is an abelian variety when it is projective. So the polarization is just the, I mean, there are different descriptions of a polarization on an abelian variety. What we keep in mind is that we can embed our complex torus into some projective space. And again, we have a moduli space which parameterizes isomorphism classes of principally polarized abelian variety. When I say that they are principally polarized, I'm taking into account a specific kind of this polarization. And this is, again, an orbifold of dimension G plus 1 divided by 2. This is related to, this number is related to the fact that AG, in some sense, deals with symmetric matrices of dimension G. So this is the dimension of the moduli, of the space of symmetric matrices of dimension G. And okay, a particular example of abelian variety is the Jacobian of a curve. So we start from the object, so the curve. We consider this vector space, which is a G-dimensional complex vector space. This is a lattice inside this vector space using the fact that this is just the first homological group. So in this case, we see that a basis is provided by taking precisely the images here of these edges. Now, so we have that AI is this loop and BI is the loop going around the hole in this direction. Then we have A2 and B2 and so on and so forth. And so this is a basis of this vector space. So it defines a lattice of rank 2G inside this just by taking, this is a loop, and we consider the operator here given by the integral along this loop. And we have a natural polarization, which is provided by the intersection product. The intersection product on loop is precisely what we can imagine it to be. So in this case, we are taking its principal because the intersection of this with this is precisely this point. So it's 1 again. Here we have the intersection of these two, which is 1, while these do not intersect, so the intersection is 0. And so, yeah, this is the way to produce a polarization on the Jacobian. So a Jacobian is an abelian variety, principally polarized. Okay, so we have curves, we have Jacobians, and another way to produce abelian varieties is considering coverings of curves. So suppose to take a curve, so C tilde for me is a curve of genus G tilde, and I consider an automorphism sigma of order D, which is acting on the curve. So it's just moving my points on the curve. And C is the quotient. So if I take a point in C, the pre-image is given by the all points that are moved. This is the orbit space. So if we fix a point on C tilde, then we have a point x, then we have sigma of x, sigma square of x, blah, 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 up to sigma d minus 1 of x. And these are the points in the pre-image of the point, let's say the class of this orbit in C. So if we focus on these kind of maps, so in these coverings, so we can imagine them, I take the assumption cyclics are ramified, the greedy, so every point has the pre-images since it is unramified, so locally it is an homomorphism. And again, we have a moduli space, and this is the standard notation. Actually, there is another one which is equivalent, which says that all the data of a covering of the greedy, cyclic and ramified, is is resumed into this pair where C is a curve in genus G, and this is a subgroup, a group, let's say, isomorphic to ZD, which is given by taking points here. This notation means that I'm taking a point which is the torsion. So since here I can sum points, I'm saying that if I sum d times my point, then I get a 0. And this description of this moduli space is useful to see that it is an orbifold of dimension 3g minus g, because 3g minus 3, because we can see that if we consider the map, the forgetful map, from this to this, which is given by just forgetting this point, then we have that Rg is a finite cover of Mg, and so we get this structure. Okay, so we have this element, which is a covering, and we want to arrive to the definition of another abelian variety. And the first map that we need to introduce is the normal map associated with F. So the Jacobian of the curve, in some sense, parameterizes sum of points of degree 0. So the norm of a map F from J C tilde up to J of C, here we have a point here is a formal sum of points such that the sum of Ni is equal to 0. And this is mapped simply to the points given by Ni F of Di. So this is a group, and this is a group homomorphism. If we take the kernel, we have to take the connected component to the 0 since it is not guaranteed that it is connected. But if we take the kernel, this is going to be a subgroup of J of C tilde. But moreover, it is not just a subgroup, but it is an abelian subvariety. And this is precisely the definition of the prim variety attached to the covering. So it is, the prim is precisely, yeah, I already wrote it here. So it's the kernel of this norm, and it's an abelian variety of dimension G tilde minus G, since it is the kernel. So this has dimension G tilde, this has dimension G, and we have just, since here we have a polarization, we take the restriction to the subvariety and we have the induced polarization. Okay, and yeah. Okay, so now we have, let's say, three objects: the moduli space of curves, the moduli space of abelian varieties, and the moduli space of coverings. And we want to relate them using some maps. So the first, which is very classical in algebraic geometry, is the Torelli map. So it takes a curve and it sends it to the class of the Jacobian together with the polarization. And it is known that it is injective. Actually, it is an immersion outside the hyperelliptic locus, okay? But so we know that it is injective and it is dominant. So the image is dense in a G for genus G up to 3. So the general principally polarized abelian variety is a Jacobian. So this is very useful. I mean, if we take an abelian variety of dimension up to dimension 3, then we know that it will be the generic one. It will be a Jacobian. And yeah, then we have the prim map, which has been first introduced by Mumford. So it is the map that goes from Rg, which is the moduli space that parameterizes coverings ramified of degree 2, and we take F and we send it to the prim with the polarization as an abelian variety principally polarized of dimension G minus 1. So plenty of authors study this map in the sense of trying to characterize if it is injective, if it is, and it is known that it is not injective, but it is generically injective when it is dominant and so on. And so also for genus G up to 6, we know that this as dimension is bigger, the dimension of this is bigger than the dimension of this, so we will have positive dimensional fibers, and other authors try to characterize geometric properties of these fibers. And the point is that, again, this is useful as it is that one, because we know that up to genus 6, it is dominant. Oh no, here is a typo. I should have written prim. So what I want to do is that if we take, I mean, using this map, we are able to say that if we take the generic abelian variety of dimension up to 6, then we know that behind we can consider some covering, so some geometric objects, which are very useful in trying to study the abelian varieties. And so finally, we arrived to the main problem that I want to discuss today, which is related to a specific kind of coverings and the prim varieties associated with this specific kind of coverings. So the question is, what about d greater than 2? Because I said that in the case d equal 2 is very classical, but the case d greater than 2 is not that classical. I mean, there is not a lot in the literature. So the point is that in this case, in this work in collaboration with Carlos Naranjo and Ángela Ortega at Humboldt, we focused on the case of coverings of degree 2 of curves of genus 2. Assuming that the covering is cyclic and ramified. So the point is that in this case, we have a picture which is very interesting. It's very involved, but very interesting. So remember, we have an automorphism of order D, which is acting on C tilde. And yeah, okay. Then we know that the curve C, since it has genus 2, is hyperelliptic. The fact that it is hyperelliptic, it means that it has an involution. So this is a map of degree 2, an automorphism of degree 2, which is acting on the curve, such that the quotient is P1. But the main property that I want to use is that here we have this involution, But since the covering F is a ramified and cyclic, we can lift the involution to C tilde, to another involution, J, which is acting on C tilde. So we have on C tilde now sigma and J that are acting. And it is known that the two are two generators of the dihedral group of order D. So what we obtain is that we obtain a bigger group of automorphism acting on the curve C tilde. And we want to use these because now we have 2D automorphisms that are acting on C tilde. So we obtain new curves in the picture. So the picture is the following. This is C tilde over C is the map I started with. So the grid D coverings. This is the hyperelliptic quotient. So here, this is precisely the quotient obtained by the action here of the hyperelliptic involution. I said that the hyperelliptic involution lifts to C tilde, and then taking all the quotient by C tilde, quotient by J, C tilde, quotient by J sigma, so on and so forth, C tilde, quotient by J sigma D minus 1, we obtain all these intermediate quotients. They are all curves of genus K, and yeah, the map pi 0 is of degree 2, and this map is of degree D. And the point is that having this nice picture, we can, our goal is to study the prime attached to this covering. So having all these curves, we can use them to study the prime attached to the covering. So we have that first, the prime is inside the Jacobian of C tilde. In C tilde, we have the automorphism sigma that it is acting, and it is possible to show that this automorphism actually restricts to an automorphism of the prime. So we are getting an abelian variety which admits the action of an automorphism of degree D. Then, as I already said, all the curves Ci are isomorphic. The map pi I, which are the maps here, are ramified. So since they are ramified, we get that the Jacobian of these injects inside the Jacobian of C tilde. So we have a lot of Jacobians inside this prime. And it is very nice because on the prime, there is the action of sigma. And this action is such that all these Jacobians are moved. So if we use sigma or powers of sigma, we can send all these Jacobians, we can move all these Jacobians. And in this way, we are able to say that there exists an isomorphism as polarized abelian variety. So the prime is isomorphic to the product of these two Jacobians, and with a particular kind of polarization here, which is, I mean, okay, it has to be. But what we obtain is that, okay, this prime is isomorphic to this product, and we want to use this structure to study it. And also, furthermore, we get that all these automorphisms that are automorphism on P actually restricts to automorphism of this Jacobian. And this is remarkable since we are dealing with abelian varieties whose endomorphism algebra is richer. Usually the endomorphism algebra of an abelian variety is just that. Here we are dealing with something which is richer. So it's interesting. And so the final map is the prime map attached to this particular kind of coverings. So it is defined from the moduli space of degree D coverings of curves of genus 2, and it maps inside A delta D minus 1 ZD is the moduli space of abelian varieties of dimension D minus 1. Delta is the type of depolarization. It's not principal, so it's different from the classical ones. And the ZD means that I want to recall that on the prim, I have the action of an automorphism of degree D. And yeah, the point is that this map was not studied a lot in the literature. So there is, in the direction of saying something relating to is injectivity, is generic injectivity, or the subjectivity, there is this result by Albano Pirola, which says that the generic fiber is positive dimensional in case of D equal to 3 or 5. A work by Lange Ortega characterizes the case in which the map is dominant onto this image and is dominant onto a D minus 1 delta blah blah, and it has generically degree 10. And yeah, what we did is we studied all the, let's say, a lot of the remaining cases. So we proved together with these two authors that it is generically injective for every prime D, such that if we say that K is defined as D minus 1 divided by 2, we ask that K is prime 2. So at that point, when we prove this theorem, we ask ourselves, okay, are we giving this characterization for a finite number of cases, or is this an infinite number of cases? And we discovered, this is nice, I think, we discovered that it is a conjecture by Sophie Germain, which says that there are infinitely many pairs of prime numbers of the form K to K plus 1. So this is the theorem, and